Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue on the discussion on filter design. For this video, I'm going to concentrate to discuss how we can design a top C capacitive coupled to resonator. Earlier on, I have done a video to discuss the difference between top L and also top C. So for this video, the objective is to discuss how can we design, which in turn how to calculate the L and C value in order to achieve a top C coupled to resonator. This will be the part 11 series discussion on filter design. The earlier on series discussion on filter design, I have put the video list, okay, which is under the playlist, under the description. So please take a look on those videos if you're keen to know more about filter design. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Once again, sincere thanks for your strong support. I really appreciate that. Thank you so much, guys. Before we start, okay, let's discuss when or why we need to use top C coupled to resonator. Okay, I'm not sure whether are you able to recall what is low side injection and high side injection. In fact, I have done a video to discuss when we consider it low side injection and also high side injection. Okay, I will put this video link under the description too. So please take a look on this in order to understand what is low side injection and high side injection. But in short, for low side injection, the FRF will be bigger than the FLO, okay, which means that the image has the lowest frequency. As for high side injection, okay, you can see that my FLO is actually higher than FRF, okay, which means that the image has the highest frequency. So this is what we call a high side injection, and on your left will be a low side injection. Okay, we know that the image is something we call it undesired, and we actually want to suppress the image. In signal, we basically just want to obtain the information from my FRF. The image actually create a disturbance or interference to my FRF, and hence we need to design a bandpass filter to remove away the image on your low side injection over here, and we also need to remove away the image under the high side injection. So these two image under low and high is something that we want to remove. Next, let's talk about top C coupled to resonator. So this is why we call this top C coupled to resonator, because on the top here is basically a capacitor. So if capacitor is used to connect the two resonator together, so therefore we call this a top C coupled to resonator. Okay, so let's move on to further left. Okay, so this diagram here actually show the bandpass filter response of the top C coupled to resonator. Over here, okay, you probably see that there's overcoupling, critical coupling, and undercoupling. Okay, as mentioned earlier on, I have done a discussion, okay, what is the difference between overcoupling, critical coupling, and undercoupling. We actually want to achieve critical coupling. I have also discussed how can we avoid overcoupling and undercoupling in order to achieve critical coupling. Okay, but this is not the objective of this video. The objective of this video is to study the frequency response of a top C coupled to resonator. You can see that at the lower side, so this is the lower side, the skirt of the lower side, and the skirt at the higher side. You can see that the skirt at the lower side, basically they have a steeper roll-off factor, which means that they have a much steeper slope as compared to the high side. Okay, you can see that from the high side, they are actually much more gentle. Okay, so they decay like 6 dB per octave. Okay, but at the low side here, you can see that they basically decay at 18 dB per octave. So therefore, this low side is actually much more desired. And because of this, okay, because at the low side, they actually has a better roll-off factor. So therefore, for low side injection, okay, we actually prefer to use a top C coupled to resonator. Okay, imagine this filter response over here, so we can remove away my image and also to achieve my FRF to pass through. So therefore, for top C coupled to resonator, it is mainly applied on a low side injection. Okay. Again, later on, I also will discuss about top L coupled to resonator. But for top C, we actually prefer to implement for a low side injection because they have a steeper roll-off factor at the lower so-called skirt of the bandpass filter. Next, okay, so instead of word, okay, let me work out an example. How can we calculate the top C coupled to resonator? Okay, so this is the example here. Okay, firstly, they ask us to design a capacitive top coupled to resonator. Okay, earlier on, basically, you can see that whether is it low side or high side injection. So if let's say it's a low side injection, then we need to design a capacitor top coupled to resonator. Okay, so basically they are shown over here. So this capacitor effect basically will have a bandpass filter, and they can be actually applied at the front end of a typical VHF, very high frequency receiver. Okay, we are also given the specification of the resonator as following. Okay, so we have the source resistor 1000 ohm, load resistor also 1000 ohm, resonant frequency 165 megahertz, and we are also given the bandwidth, which is 10 megahertz. We are also asked to assume that all the components are lossless. Okay, so what does this mean? Okay, if you still remember, we have also discussed on the characteristics of inductor. Okay, you know that inductor don't really behave purely as an inductor. There will be also a resistor loss, and they also will have a capacity effect. But for this question here, okay, we are going to omit all the component loss. Okay, so this is what it means. So therefore, this will behave purely as an inductor, and this will be purely as a capacitor. So we assume that all the components, they are all lossless. Let's start. How can we design the L value and also the C value and also the coupling capacitor? How can we calculate the values? Okay, so this diagram here shows the top C coupled to resonator. Okay, from here you can see that there are actually two resonators. Okay, so this is what we call a resonator 1. This is what we call a resonator 2. So they are separate by this decoupling capacitor. You can also see that the resonator actually is a parallel resonator because R, L, and C, they are basically connected in parallel. Same as resonator 2. Okay, you can see over here, C, L, and R, they are basically connected in parallel. Okay, we also have this circuit Q, okay, which is the overall circuit Q. Okay, so this is the overall Q of the circuit. So this is what we call a circuit Q. And basically, we also have a first resonator Q, okay, which is the so-called single resonator, the Q factor, the quality factor of the single resonator. Okay, so let's start to do the calculation. Okay, so in the question, we are given the resonant frequency is 165 megahertz, and we are also tasked to design a bandwidth of 10 megahertz. So from here, okay, we can calculate the the quality factor of the two resonator or the circuit Q. Okay, because this is the overall circuit. Okay, overall circuit, we need to achieve the total or circuit Q. Okay, so from here you can see that the formula is F0 over bandwidth. If you still remember, we also talked about F0 over F2 minus F1. It's the same. So from here we can compute what is my circuit Q. Okay, so I'm given F0, the resonant frequency, as 165 megahertz. Okay, the bandwidth is given to me, which is 10 megahertz. So from here, I can calculate my circuit Q as 16.5. Next, okay, I can also calculate the single resonator. Okay, remember earlier on, okay, I mentioned that this is so-called a single resonator. So this is the overall circuit Q. So next, we are going to calculate one resonator. What is the quality factor? So from here, you can see that basically what I need to do is basically the circuit Q over a constant number, which is 0.707. This will allow us to find the Q of a single resonator. So from here, I actually calculate what is the Q for a single resonator. So simply is using the circuit Q over 0.707. So I will be able to obtain a single Q resonator. Okay, next, okay, basically, let's just do the computation on the resonator 1, okay, which is over here. So let's do this calculation on resonator 1. So I have able to find what is a single resonator Q, okay, which is 23.3 here, if you see here. So from the equation, you also know that for a parallel resonator, is actually Q equals to RP over XL. So I have also discussed how we actually arrive at this equation on my previous video. Okay, again, take a look on those videos, okay, in order to understand how can I actually arrive at this equation. So over here, this Q I already know, which is 23.3. RP, okay, for this case here, my parallel resonator is actually my source resistor, which is also 1000 ohm. So therefore, I only left unknown, okay, which is my XL. So I can actually calculate what is the value of my XL by rearrange the formula as shown over here. So from here, I can compute that my XL is equals to 42.9 ohm. Next. Okay, so we need to take note this. So this resonator 1 and resonator 2, they are actually symmetric. Okay, so we are designed as symmetric, so which means that my L1 is equals to my L2, my C1 is equals to my C2. So basically with this, we can actually design resonator 1 and resonator 2 as symmetric. And once they add resonant, okay, so basically XL1 is equals to XL2, which is also equals to XC1 and also XC2. So remember earlier on, we have calculated what is my XL. Okay, so we left this 2 pi F naught L. Okay, F naught we know, which is 165 megahertz. So from here, what I really do not know is basically my inductor value. So what I need to do is I shift my 2 pi F on to the left, okay, which I actually achieve this equation here. Okay, so I found this earlier on, which is 42.9. Okay, so if you not, you can take a look over here. So this is what I found earlier on, which is 42.9. So I put it here, 42.9. So this 2 pi F, okay, the resonant frequency is 165 megahertz. So from here, I compute that my inductor, which is 41.4 nanohenry. Like what I mentioned earlier on, resonator 1 and resonator 2, they are symmetric. So L1 and L2, they have the same value, which is 41.4 nanohenry. So next, okay, we also can calculate. Remember, since at resonant, XL1 is equals to XC1, so they are exactly the same value, which is 42.9. So again, from this equation here, what I do not know is basically C1. Okay, so I can calculate my C1 value, okay, by rearrange the formula. Okay, so the rest of 2 pi F, I just 1 over, okay, 2 pi F XC, which is shown over here. So 2 pi, I already know my resonant frequency, which is 165 megahertz. Okay, XC, which I have found earlier on, which is the same as XL, so which is 42.9. So from here, I can calculate that my capacitor is 22.5 picofarad. Okay, again, like what I mentioned earlier on, resonant 1 and resonant 2, they are similar. So therefore, C1 is equal to C2, which is 22.5 picofarad. Next, what I need to calculate is basically the decoupling capacitor. Okay, so this is the equation to calculate the decoupling capacitor. C1 value, which I have calculated earlier on, which is 22.5 picofarad. What I need to do is basically I divide by a so-called a single resonator Q, which is 23.3. So from here, I can calculate that the decoupling capacitor as having a value of 0.96 picofarad. Okay, so next, I just put everything in one page here. So this is what I'm given. Okay, I'm given, and basically this is my proposed solution in order to achieve a bandpass filter that having a resonant frequency of 165 megahertz with a bandwidth of 10 megahertz. So these are all the values that I have calculated. And so basically, this is how we can design a top C couple 2 resonator. Okay, with this, I'd like to end my discussion. Please help to like and subscribe. Once again, sincere thanks for your strong support. See you guys.